Dear friends, I will start the part 2 of our time capsule project presentation for the Sri Lankan Geotechnical Society. In the part 2, I'll be covering about reduction of the landslide hazard zonation and monitoring under the general topic, reduction of landslide risk in Sri Lanka. The landslide disaster risk reduction was done in 3 stages here. First, the risk identification, risk communication, and risk mitigation. Under the risk identification, we have developed hazard zonation maps. In BRO, the main government organization in charge of landslide risk reduction, has developed hazard zonation maps for the critical districts in Sri Lanka. I will elaborate on that. Then we have conducted site-specific investigations on critical sites, detailed investigations to identify the risk and mitigate them. Then these identified risks were communicated to the stakeholders. Through that, we use monitoring of rainfall factors such as rainfall and other changes that rainfall is inducing in the ground. And based on the monitoring data, we issue early warnings. And also people in the regions were educated about the initial signs of a landslide and what actions are to be taken, and they are prepared on that. So that's the risk communication with the objective of minimizing the landslide risk. Then there are risk mitigation measures adopted. That is, first, development control. That is, in the areas with significant land rise risk, new projects were carefully thought about, right? So the NBRO scientists, that is, who are geotechnical engineers and geologists, advise the levelers on their projects, how to do it without creating additional landslide risk. Then land use planning, as there is, what are the various land uses that can be permitted in those areas. Resilient construction, how to do the construction with minimum disturbance to the land and therefore minimizing the risk of landslides. And special investigations and design of countermeasures with special slopes which are with high landslide risk, especially in the transport network and in close proximity to schools and other the developments. So detailed designs, detailed investigations were done, detailed designs were done on rectification measures, and they were implemented. Then on situations where there is high risk of landslide and the mitigation at the site is economically not feasible, people were resettled on different areas which are much less vulnerable. So coming to the landslide hazard zonation in Sri Lanka, this is a project which started with UNDP assistance in 1990. It went on with their assistance up to 95. Thereafter, Sri Lankan government has taken over. The maps of 1 to 50,000 and 1 to 10,000 scales were developed to cover the 13 critical districts in Sri Lanka. 1 to 50,000 maps are completed now, but 1 to 10,000 map the preparation is still in progress. So you can see the critical district where there is more susceptibility to landslide. So these are the regions where the maps are available. So this is a complete picture of the 1 to 50,000 zonation maps. So different risk zones were here. The light green where landslides are not likely to occur. The light yellow modes, there is modest level of landslide risk, and the much darker green, brown is landslides are to be expected. Dark brown is landslide are most likely to occur. So the regions by field observation and available printed data as well. So the geologists and geotechnical engineers visit all these zones and make the assessment to do this zonation. So the details of which are presented in this slide. So these are the terrain factors used in coming up with that zonation: bedrock geology and geological structures, types of natural soil and the soil cover, soil thickness, slope range, hydrology, land use management, and landforms. For each terrain factor, there is a particular score given. The relative values of these scales were decided on the experience and other statistical sort of principles, and the detailing of this particular terrain factor. For the details, guidance as how to assign the terrain factor is presented in this table. So you can see the sub-factors involved in each terrain factor. And so for each different region in the particular area, the data are obtained, people visit it, observe the features, and based on that, certain appropriate numbers were assigned. So with that, you get a particular score. So as illustrated in this one. So in this particular location, so these are the terrain factors and these are the scores assigned, right? So it got a total score of 55. So landslides are likely to occur. That you saw that in the legend in the previous one. In this particular location, so these are the terrain factors, the values for the terrain factors. It has a value of 71 out of 100. So landslides are to be expected. So you saw the legend in the previous one. So maps like that were developed for 1 to 50,000 scale for all the 13 districts completely, and 1 to much finer maps to scale 1 to 10,000 are currently being developed. So these maps are freely available to be used for in various development projects. National Planning, Physical and Planning Department, UDA, Road Development Authority, local authorities in landslide-prone districts, and the Central Environmental Authority are making use of these maps in their development projects. In addition, any private developer who is involved in proposed development in this area can get the NBRO assistance and get these maps and make use of that in the decision making in their projects. Showing further details as how well this had been predicted. So there is in some recent landslide, this Aranayaka landslide. So that is the zonation. That is the zonation. It indicates landslides are to be expected in here. So this is the area where the landslide was triggered, and then the debris flowed down in this path. Now, this hazard zonation maps predict the initiation, the susceptibility areas and initiation areas of a landslide. Currently, there are studies done to establish the flow area, runout areas of the landslide as well. So these areas, as you see, are with lower landslide risk. That green areas and the light yellow areas and so forth, these are with much lower landslide risk, but the people in these areas are at risk because of the debris flow. So now current work is to identify the regions of region where the debris flow will cause disturbance. So the landslide at Ayagama was also identified in the hazard zonation maps. Similarly, in Asanagula, this is the initiation area, and what is marked by red is the complete flow path. So the initiation areas were identified. Right. We said that earlier, the landslides in Sri Lanka are triggered by excessive rainfall. So it is very important to monitor the rainfall in critical areas. So at present, NVRO has installed more than 325 automated rain gauges in various parts of the critical districts. So they record the rainfall automatically, and electronically data were transferred to the central office in Colombo. So at real time, we have an idea about the rainfall pattern in throughout this area. With this rainfall, the landslides are triggered. Currently, there are some threshold rainfall values decided based on the experience. So if the rainfall within past 24 hours is exceeding 75 millimeter, people in the area are advised to be watchful. If it exceeds 100 millimeter and still continuing, they are alerted that a landslide is likely to occur. And if the rainfall within last 24 hours is exceeding 150 millimeter and there is rainfall of the order of 75 millimeter within 1 hour and still continuing, then people are requested to evacuate from these critical sites. Now, so these warnings are these numbers, the rainfall threshold rainfall values were decided based on experience. With what I presented in part 1 of this series, we can show that the threshold rainfall value for a particular location is site dependent. We can establish that by modeling the infiltration process and see how the Porpoise regime changes with the ongoing rainfall. So ideally, threshold rainfall values should be established locally, and more reliable evacuation processes should be decided. Currently, NVRO is working on that target, trying to establish threshold rainfall values for the areas of different level of susceptibility in the country. Now, these rainfall records, rainfall monitoring data are sent from various regions to the central office, and then they are transmitted to the disaster management center. So NVRO, in collaboration with the disaster management center, issues warnings to the people through radio, through various other media, telephone, and police and other government officers, right, are used to communicate that to the people in the region. Then evacuations may take place in the vulnerable communities through that. Then coming to very important landslide runout assessment, that initial the hazard zonation project predicted the area of initiation. And as I showed in the previous slides, the debris were flowing through blend of much smaller slopes, lesser slopes of lesser gradient, and even coming to the flatter land. So therefore, it is very important to identify the runout areas. Right? So usually in these flatter lands, there may be high population, right? So the flow initiated at a high velocity, maybe high at the higher ground, may be moving at a rapid velocity, causing much distractions there. So runout assessment is therefore critically important, and studies are underway at present for this purpose, on this purpose. So the runout assessment can be done empirically. So there are some empirical methods currently we are testing out, or analytically by closed form equations or by numerical models. So this study is currently going on. For the recent landslides, we know the initiation area and we know the runout area. So they are in the actual landslides, runout areas are clearly plotted for the landslides that happened within last decade or so. So we can do these predictions using these different methods and compare that with what actually has happened. So with that kind of a back analysis, we can establish what are the most appropriate techniques to do the runout assessment based on the availability of data and the terrain conditions. So we can establish what is most appropriate in that case. So therefore, we can develop complete risk maps identifying both the initiation area and the runout area. So these are some further details of ongoing work on that in the Saranaka landslide. So you see the initiation area and the flow area. So these software were used in establishing these runout areas and comparing with the observations. So coming to some further details of this Aranayaka landslide, which occurred on 17th May 2016 in the evening, destroying 76 houses and causing 129 deaths. So that was the initiation area, and the debris flow went on for 2.3 kilometers. So this is the rainfall record preceding the landslide, right? So you have here plotted the daily rainfall and accumulated 3-day rainfall. You see that the landslides are triggered with some prolonged rainfall. So these are threshold rainfall values, which the 3-day the accumulated rainfall was 450 millimeter in this particular case. So with the, as I mentioned earlier, we are trying to establish these values for different regions through our analysis. So getting into further details of this Aranayaka landslide. So this is the initiation area. So that is the flow path. The debris are flowing into areas of low initial landslide risk as seen here. The width of the crown of the landslide is about 345 to 350 meters, and the scarp height is about 50 to 75 meters. The bedrock of the area is high-grade metamorphic rock garnered by gneiss, and there were 2 major vertical joints in this rock mass. So as you saw with the rainfall records, there was significant infiltration from the heavy rainfall that that preceded this event, and the landslide, which started as a slide, ended up as a debris flow with the presence of heavy amount of water. And these are further details, close-up details of that. So there is forest cover in the adjacent areas, and the debris flow moved down to the flat terrain, and also at the intermediate levels. There were a number of houses destroyed. Now this area remained intact. The debris flow has, I mean, it is with the presence of excess water, it has destroyed houses further down in this much flatter areas. And there were certain completely unaffected regions with the debris flow. So that depends on the down topography. The mass that initiated there has moved in 2 directions. The left side is about 75 to 125 meter wide, and the right side is about 350 to 450 meter wide. And at the lower levels, it joined as one stream and ran down to this flatter area. So the task is to, with the ground topography and the ground cover details, to initially predict what is the runout area. So with this observed runout areas, we are trying with different available models, right? How to back calculate that and how to do a better prediction for future landslide. So these are some further pictures on that landslide. So this is the terrain before the occurrence of the slide, and this is how it looked after the tragic event. Now, so that's one task ahead of us and one task that we are working tirelessly. Now, we said that the rainfall, the landslides are triggered by excessive rainfall. So there are, the rainfall is the simplest thing to monitor, but also to issue more reliable warnings, it is important to monitor other factors such as moisture content changes, matrix action losses, pore pressure developments, and the ground movements, both at the surface level and at the deeper levels that are initiated by this rainfall event. So with the rainfall event, these changes are happening gradually. Finally, it would lead to a disastrous event if we can capture these initial changes early enough. Then we can get the people to move out and minimize the damages, or even we can get into some rectification measures and prevent a catastrophic failure. So to monitor these changes happening in the terrain, the moisture content changes, matrix action loss, for water pressure changes, and the ground movements happening in the terrain, there are various instruments which need to be installed at different locations of the site. So with initial study of the likely pattern of movement and likely levels of failure surface, one can identify where are the best locations for install these different types of instruments. I will elaborate that to a certain extent in the next slide. The moisture sensors monitor the change of moisture content with time. So they are electronic devices. So the data can be acquired by a data logger and transmitted to a control central office. Similarly, tensometers monitor the loss of matrix action, and piezometers monitor the change of pore water pressure, positive pore pressure. Tensometers monitor the change from negative values to 0, and piezometers monitor the positive pore pressures. Extensometers and tilt sensors are instruments that can monitor the surface level movements with that initiation. Then there are strain gauges which are installed in deeper levels, which can monitor the movement happening at deeper levels, and inclinometers which are installed in boreholes, and through the monitoring process in an inclinometer, one can identify the failure surface, deep failure surface. So these are some pictures of how this instrumentation and monitoring work going on, done by NBRO staff at different sites in the country. The water level gauge that is installed in a borehole to monitor the water level. So if the ground is not highly variable, so this kind of thing would be helpful. But in more variable situation where the subsoil consists of different layers of contrasting permeability and shear strength characteristics, it would be required to monitor the pore pressure in different layers. So in a single borehole, one may install different types of pore pressure measuring devices at different levels. So usually we install pneumatic type or vibrating wire or electrical type piezometers, which are capable of acquiring the data quickly. So they are electronic devices, so the data acquired can be transmitted to a central office. So this picture shows some instrumentation in the Baduluthirigama landslide. I'll be talking about the Baduluthirigama landslide later as well. So with the surface features and subsoil information, landslide boundary was plotted. What is shown in red is the landslide boundary plotted by detailed field investigations. Then, now these locations SB2 and SB1 indicate the extensometers, location of extensometers. So these, and this is the central axis of the landslide, is moving down here. So these dots indicate location of the locations of boreholes for the water level meters and so forth. Now, coming to an extensometer, extensometer is a device which can detect surface level movements. I will show the details in the next slide, but here I have to say that one end of the extensometer should be in the area outside the landslide and other end within the landslide. So the device is measuring the relative movement as illustrated here. So this is the region outside the landslide, point outside the landslide. So the other end is within the landslide. So there is a wire connected to here, and the wire is protected by this the PVC pipe. And what is being measured is the movement or the extension, right, or change in length of the wire through this device. So if there is a movement in the landslide, right, so there is a relative movement between the point outside the moving mass and inside the landslide. So the tilt sensor is a device which is driven to a shallow depth, 2 to 3 meters, and it is with certain electronic instrumentation, so that can detect the surface level movement. So if there's a surface level movement, there would be some tilting, change of if there is some surface level movement, if there is a movement of the landslide, there will be a surface level movement. So that is detected by the tilt sensor. So attached to it is the moisture content sensor, so which will establish the change of the moisture content also. So this figure shows some responses of these monitoring devices for this rainfall event. Now, what is plotted here is enlarged here for further elaboration. So there is this rainfall event, and the accumulated rainfall is plotted here. And here you have the movements of the extensometers, right? So movement extensometer S2 is showing some movement with this rainfall. Similarly, S1. So these are the observations in the tilt sensor, right? Tilt sensor. So it is static here. With this rainfall event, it has started to move, and with the cessation of the rainfall, it is more or less static. And with this second rainfall event, which is of a lower intensity, there is some further movements which are much less than corresponding to the previous one. So these different devices are complementary to each other. So it confirms what is observed by one device. So in addition to the rainfall, to have some kind of devices to monitor what is happening in the soil, the change of moisture content, the initiation of movements would be very useful for all purposes. So this is an inclinometer. So inclinometer, you do a borehole and install these pipes in that to a depth below the suspected failure surface. So with the initial observations, subsoil profile and so forth, you can deduce the failure surface is probably at say 20-meter depth or whatever. So in that case, these devices, these inclinometer, you have to do a borehole deeper than that suspected level, and inclinometer tubes should be installed to a depth greater than the suspected failure surface depth. So in that, to monitor the movement, we use this probe, right? So this is the detail of the probe. So the commonly used probe is a biaxial probe which contains two perpendicular accelerometers. So with single pass of the probe, data acquired in with two passes, data acquired in 4 different directions. In one lowering of the probe, it measures the tilt in the plane of the inclinometer wheels, which are in that direction, and also other accelerometer measures the tilt in the plane perpendicular to it, right? So with lowering of this in 2 different orientations, we get all the measurements necessary, right? So you see these grooves in that. So you install the inclinometer in the site with this one line being in the direction of the axis of the landslide, and to establish the movements, we have to go to the site and lower the inclinometer in the 2 different directions and get the readings. So it cannot be done remotely. Then these are strain gauges, which are installed at different depths after drilling. So strains at different levels can be monitored by these strain gauges. Right? This shows installation and monitoring of that. So this is a complete picture of the Baduli-Sirigama landslide, the full boundary of the landslide. As I showed before, so these are the locations of 2 extensometers, and 2 other extensometers are there. There are inclinometers at BB2 and BB4. So inclinometers are mostly installed along the axis of the landslide to a depth greater than the suspected depth of the land moving surface. And then there are water level gauges, BB3, BB4, right? BB4, BB3 are water level measurements, and strain gauges at BB1, right? So this shows the full instrumented plan of the Baduli-Sirigama landslide. So this work was done with JICA assistance. This shows details of monitoring. Now, this landslide had been rectified by subsurface drainage subsequently, but these are the movements monitored by the rainfall events that occurred prior to the rectification. So this is the rainfall event in this critical rainfall event, how the movements occurred in these extensometers, right? SB1 and SB2, which I showed you in the previous plan. In SB1 and SB2, which I showed you in the previous slide, right? With this rainfall event, significant movements have taken place. There were no sort of recorded information in the other 2 extensometers, which are the top of the landslide. And inclinometer, you can see with this rainfall event, there were movements observed at this depth. Right? This is how the movement uh, initiated, the movement increased rapidly. And with the, now over here you see inclinometer tube is perfectly vertical, no deviation, but here you see the deviation has happened, the movement has happened at that depth. So by lowering the probe into the hole, you can identify at what location the movements are taking place, which is the uh, which is the location of the failure surface. Now, so this is the identification of the failure surface with strain gauges, right? So considerable cumulative displacements are located at these steps. So identification of the failure surface is critically important because when we design the rectification measures, that we have to, we need that information. Right. So that finishes the presentation on hazard zonation and monitoring. So we'll get to the third part a little later.